All right, it's 11:15. I think we'll get started. So you have a homework due on Friday, homework 2. It's a good time to print off that homework right now, take a look at it, and figure out what we're going to talk about this week or what you need to learn this week in order to get the homework. Also, you have PLAs, all the usual stuff. I will post homework 1 solutions so you can study from those. I'll post those tonight. And also I will try and open up the PLAs so you can go back and study the PLAs. Don't bother turning in PLAs late because I get to see that on Canvas, but I want to open up the PLAs so you have some study material because the first exam is next Wednesday. And so we're going to have 3 regular classes this week. We're going to finish the information on Monday and do a review on Monday. So I'm going to tell you exactly the topics that are on the exam. It's going to be super clear what material's on there. And then the exam is given on Canvas on Wednesday. We won't have an in-class meeting, but you will have a Canvas exam that you can take anytime between like 7 a.m. and 11 p.m. But it's both multiple choice on Canvas, and there will be a written section that you have to fill out or just write on a piece of paper. I really don't want that one done on an iPad. So blank piece of paper, and you can say written question 1, here's my answer. Written question 2, here's my answer. You can scan it or take a picture of it with your cell phone and then submit it to Canvas a reasonable amount of time after you finish the multiple choice section. And so the multiple choice section, you get 70 minutes. It's time. Canvas will stop you. And like half an hour after I see that you've finished the Canvas exam, I want you to submit the written part. So I'll give you a little time. You have a little leeway on the written part. That's fine. I know you all are taking care of your academic integrity, but I don't want the written part submitted like 4 hours later. Everything is logged on Canvas, so I get to see how much time you're taking, which is fine. That helps me figure out how long, how hard the exam was, or, who raced through it quickly and got a perfect score, who finished it in 5 minutes and got 2 right. I like to see stuff like that because that gives me some clues as to your performance in the class. But you should set aside at least like an hour and a half to get everything on the exam done. Like I said, Canvas will kick you out after 70 minutes. That's that. And then you'll have the written portion. And it's not overly long. It's not going to be tons and tons of questions. I think it's 20 multiple choice questions, but it's going to be very specific to the things that we've talked a lot about in class. And so you want to be really comfortable with the homework. You want to be comfortable with the key slides. You want to be comfortable with the key concepts in the PLAs. And if you focus on that stuff, you'll be wildly successful on the exam. But this week's a regular week with homework. Any questions or comments? Yes.
So within the multiple choice,
It's separate. So do the multiple choice first, because as soon as you click start the exam, Canvas is running the clock. So you finish the multiple choice first, submit your answers, or however it looks like, I'm done with my exam, click that, and then go to the written section. Yeah, and I'll provide explicit instructions. I'll also have some more office hours before the exam. So I'll have some more office hours next Monday, some more office hours on Tuesday, but there are no questions allowed on exam day. So I won't take any questions on Wednesday. So up to about, 8 or 9 p.m. on Tuesday, you want to make sure you get as much help as possible, because I won't even answer any emails. I won't answer anything on Wednesday to make sure it's fair. One of the keys with getting Canvas to work right is to use the right browser and to hit reload. So sometimes on the PLAs, the diagrams don't show up. If Canvas has a problem with the query, if it's not fast enough to pull up the figure from the Canvas database, wherever that lives, it just shows a blank thing. You can reload, or you can hit that little, circular arrow thing in your browser as many times as you want to get the pictures to reload, and you're not penalized for that on Canvas. So if the pictures don't reload, sometimes you have to, or don't load, sometimes you have to reload it 5, 6, 7 times to get Canvas to wake up. That's fine. There's absolutely no penalty for that. So don't email me on Wednesday saying I did poorly on the exam because I couldn't get the pictures to load. You've been warned. You practiced it on the PLAs. Every once in a while, something gets super off track on Canvas. We'll fix it after the exam. I mean, I'm not going to hang you out to dry, but be savvy about that. And my real advice is use the right browser, be in a place where there's fast internet, somewhere on campus, you know, as quiet a spot as you can find to do that. This room will be empty during the exam time because we're not going to be meeting. So feel free to use it. I will not be here, but you're welcome to sit in here if you want. But make sure that you're in a good spot. You have fast browser, you have the right setup, you have a pencil and paper so you can take scratch notes, and make sure you use the reload. That's one of the key stopping points that we've had in the past. Yes?
Will we be on Zoom for the exam?
Nope, it's not proctored. I know you all know how to do academic integrity. I will have some notes in the exam instructions as to what you're supposed to do. You'll be schooled on that on Friday and Monday during the review, but it's find a good place, get a paper and pencil in your laptop, and take the exam individually. Yep. Yes.
Are you going to unload practice exam?
Good question. I will have a practice exam and I'll probably put it up on Friday. Yeah. So that's my practice exam. It gets you used to how I'm going to ask questions because it is multiple choice. You know, it's a little bit different than the homework. If you want more questions or if you want extra studying, there's questions in the book. There's lots of polymer science questions online. You have to go out and find that extra material. There's other polymer science books. I don't have a huge database of questions that I sort of circulate, but the practice exam is a good example and reflective of what you're going to see on the real exam. Other questions? Great. Okay, this week is the week to get super comfortable. And you notice we only have 2 homeworks and 7 PLAs before the first exam, right? And so the amount of material, or at least the key concepts, lots of them are new because you've never taken a polymers class before, but they are a slice of polymer science. You know, the exam's not going to be hugely broad. It's going to be on the things that I ask you a lot about. And so concentrate on some of the things we talk about a lot and the things I've asked you questions on. Those are probably the important stuff for the exam. All right. Also, all of the slides are uploaded for up to the first exam on the OneDrive. So go download the slides, the study guide's even up. That's slide set 9. So you can check that out and start to think about that. And I'll show you that as we get further this week. All right. So we've talked a lot about step growth and chain growth, or addition and condensation polymerization. You really need to know which one is which. You need to know the key functional groups for each. And we also talked about the molecular weight buildup for the 2 types of mechanisms. So remember, in step polymerization or condensation polymerization, we have this slow molecular weight buildup. So what's important when you see a plot like this is you say, okay, what's on the y-axis? That's molecular weight of the polymer chain. Okay, I got that. Okay, what's all right? I think we're back. Hopefully my recording is not all goofed up, but there's no guarantee of that. So anyway, we have the slow molecular weight buildup in step polymerization. And what we thought about last time was step by step by step, it's slow. Condensation polymers, when you're making those small molecules, it takes time for those reactions to happen. And so that's why step polymerization is generally a slow molecular weight buildup, and we'll go more into that. Chain or addition polymerization, remember we used vinyl monomers. So we used monomers with carbon-carbon double bonds, and all we did was move electrons, right? All you do is take one electron one way, one electron the other way. In addition or chain polymerization, it's like a fast chain reaction. So molecular weight increases quickly, and the x-axis on this plot is usually extent of conversion or extent of reaction or just conversion. And it goes from 0, which is all monomer, to 1, which is all polymer. We'll define conversion as we go on. You can also think about it as time, right? It takes time for monomers to be turned into polymers. And in chain or addition polymerization, that happens really fast. That's why the curve climbs quickly. So you get to high molecular weight at short times or small conversions. Whereas in step or condensation polymerization, it takes a while. This is a key plot. Make sure you can draw it. Make sure you can describe it. Make sure you know what the X and Y axes are. Make sure you know what these two curves are. And then you'll have some of the basic concepts, and we'll keep going on this. Any questions? Okay, concerning molecular weight, we've talked about a number of different ways to describe molecular weight and how to get M0 the copolymer, how to get M0 the repeat unit, what degree of polymerization means. And so I'm going to give you a set of equations that you'll get to use on the exam that you can describe molecular weight using these different equations. And so this is the easy one, right? Molecular weight of the chain equals degree of polymerization. Make sure you know what that is. It's also the same as N times the repeat unit molecular weight. And you know that we principally have two different types of molecular weight, an MW or a weight average, and an MN, which is number average. And because of that, you know, the repeat unit molecular weight doesn't change, right? M0 is what it is. You just need to know what the polymer is. But you do have an XN and an X sub W calculated from the number average or weight average. It's a lot easier to think about this one because this is just the numerical average, right? That's the one that you can count up very easily. Weight average has other stuff going on, but make sure you have some of these equations and know how to use them. Here they are right here. And then the key other thing we have to add is the dispersity. And it's always MW over MN, no exceptions. And so that sets the limits that dispersity has to be 1 or above, can never be less than 1. Okay, these types of molecular weight questions you'll get to practice on the homework. You had some on homework 1, you'll have some on homework 2. There are some examples in the slides. And so make sure you can do these calculations quickly, especially things like this, where I give you a set of molecules, or I give you, 10 grams of this, 5 grams of that, and you can calculate the MN and MW. You've already practiced that. Yes?
No, well, we let me use like programs like Mathematica or Python or MATLAB for an exam.
No.
No?
Calculate, you won't need to. Calculator, pencil, paper. That's it. It will be faster to just write this down and use a calculator to get it than to do it in MATLAB or Python. Now, you want to use those if we have mega distributions or you do that sort of stuff in your research, but it'll be much faster just to do it by hand. You don't want to goof around with that stuff during the exam. Yes?
Do I need to know Z average?
So we are not going to talk about Z average, which is the third moment. So it's useful to know that MN is the first moment of the distribution, MW is the second moment, and there's something called the Z average molecular weight, which is the third moment. It just continues to describe the breadth. And so you could come up knowing that it's the third moment, or wherever our moment equation, well, we can go back here. Knowing that it's the third moment, it would be tricky if I asked you, okay, knowing that MZ is the third moment of the distribution, what does its summation equation look like? But I won't ask you that. So you can ignore MZ. But if you do research, or if you do a lot of work on molecular weight, you'll run across it. Any other questions? Okay, practice this stuff, know how to use these equations, because the molecular weight questions should be pretty easy to plug and chug as long as you keep your wits about you and you remember some of these things. And you'll have these equations on the equation sheet on the exam that I will give you. All right, so everyone's heard about plastic pollution. That's no secret. There's a lot of plastic in the ocean. They say that there's more plastic litter now than all the biomass on Earth, except for trees and bacteria. And so that's really interesting. And it's interesting to think about the lifetime of trash. So anytime you build something, you build a cell phone, you build a building, you make a car tire, any sort of product that you manufacture is going to have a certain life. And eventually, you're going to have to throw that away. So even this building someday will have to be recycled. It's not going to stay forever. And so depending on how long something lasts, you could see that packaging, which is mostly made out of plastic, doesn't have a very long lifetime, usually less than a year, right? Consumer and institutional products, so things that people use last couple years, your computer, things like that, all the way up to buildings. And so we've got to think about what to do with all this trash, because we can't just put it in the landfill. Otherwise, all we're doing is making stuff and eventually just shipping it to the landfill. We're going to run out of landfills. There's big problems with that. And so we'd like to think about how to accomplish a circular economy. And this is a big keyword if you're interested in sustainability, or if you're interested in environmental issues with materials. A circular materials economy, a circular economy, and certainly a circular plastics economy is a really interesting concept where you could take, whatever thing you're interested in, some sort of raw material, polyethylene, or whatever your plastic jug is, and you can bring it back and not only recycle it to a park bench or recycle it to some other product, but actually recycle it right back into the product of interest. That's what circularity means. There's the terms called upcycle, which means you go up the value chain. So you take a plastic cup and make it a cell phone case. And all of a sudden, that 1 cent plastic cup becomes a $20 cell phone case. And so that's upcycling the value chain. Excuse me. That's not as common as downcycling, where you take a cell phone case and turn it into a park bench. And so that park bench may last longer, right, than a cell phone case, but eventually you're still going to have to throw that park bench away. So you have to take that park bench and be able to turn it into something else, or turn it back into a park bench and go around and around and around. And this is what society, and this is what the plastics industry is really struggling with right now. How do you take laundry soap bottles and sandwich containers and used masks, which are all plastic, right? And how to turn those things back into either the same product or valuable products. And so we're hoping that by really working on this problem with the plastics we have now, but also with designing future plastics, so the plastics of the 21st century that are designed to do this circular economy, we'll be able to start to make some headway on the plastic pollution problem right now. Yes. So upcycle means you're going up the value chain, more valuable applications, and downcycle means you take something of moderate value and it just goes down, down, down to less valuable applications. Any other questions? All right, you might see that. This is how polymer science is going to be done from here forward. Okay. Now we go all the way back and find this. Okay, you'll notice there are repeated slides in the slides, and it's to remind me to mention stuff. It's to remind you of the important stuff. But if you're really studying and trying to figure out what's going on, it's okay to download the slides and make your own slide deck. That's fine. Delete all the repeated ones, but the repeated ones are in there just to make sure the flow of the class is reasonable. Okay, so we've talked about this before, so make sure that you're up on all these vocab words. Sometimes you'll see polycondensation or condensation. They mean the same thing. We all know what poly means, or polyaddition versus addition. And so make sure especially that you can identify what the polymer is from the functional groups and the method of how to make that polymer from what the polymer looks like. And we're going to continue to talk about key features of both of those. You had a homework problem on skeletal structures, right? Ethylene glycol diacrylate makes branched or cross-linked skeletal structures, and I'll tell you why in a second. And methyl methacrylate makes linear polymer structures, and I'll tell you why in a second. We're going to talk about equal reactivity, and we already talked about the mechanisms. We're going to keep talking about that. Okay, so we already covered this, right? And you should be able to draw this out. Conversion time. Conversion, let's say, or time. And you know that step growth is like this, chain growth is like this. What's wrong with this plot? Yes.
No y-axis label.
There's no y-axis label. And so if you do it like this on the written part of the exam, you will get some points off. Just like units, if you don't have labels on the graph, I don't know what you're graphing. Now, sometimes you'll be able to say, okay, I know conversion is between 0 and 1. Molecular weight, I'm not really sure how big the polymer is, right? Maybe in general, this is like 100,000 grams per mole. You really want to put the units there to make it perfect. But it's not 100, right? We don't make polymers with molecular weights of 100 grams per mole, right? That's a monomer or a repeat unit molecular weight. So sometimes you can put the numbers in there. Sometimes you don't have to, just make sure it's reasonable. But you notice that I can draw out that answer in 2 or 3 minutes. And so if you remember some of these concepts, chain reaction is fast, I know what a fast molecular weight buildup curve looks like. And step polymerization is slow, I know what a slow polymerization curve looks like. And the key is that this is an asymptote at conversion equals 1, which means this actually goes to infinity. And I'll show you the math in a second, either today or tomorrow when we get to it. Okay, so how do we actually make a polymer chain? Remember, we're always making chains of some kind, whether it's a linear chain, a branch chain, a cross-link chain, but we need lots of these monomers to line up. So in organic chemistry, you studied a lot of, say, this AB reactivity, right? So there's some R group, and let's say it's connected to an alcohol, right? And then you have some carboxylic acid that's connected to some R group, right? And you take that alcohol and carboxylic acid and you react it to form a what? Ester. So AB is now an ester. So it's ROC And we get there because remember, what's the small molecule byproduct that's spit out? Yep, minus H2O. I know some of you are a little hesitant because you really want to put two oxygens next to each other, right? You really want to form O carbonyl, but that we don't use that group in polymers. That's something else. We really are looking for esters, and so that recall should be quick. And so when we do this reaction, we just connect these two R groups with an ester, and that's it. So we haven't formed chain. We've only gone from the molecular weight of this thing plus the molecular weight of this thing to something that's got double the molecular weight, and that's not a polymer. And so what we need is we need repeated reactions. The reaction has to happen over and over and over and over to get degrees of polymerization of 500, 300, 800, 10 degree of polymerization of 5,000. And the only way to do that is to put a functional group at each end of our two molecules, R1, R2. And now you'll notice that we get R1, R2, connected back to R1, connected back, this one's going to be R2. And so we're making esters, if you take the previous case, over and over and over. So the degree of functionality has to be 2 or greater to get a polymer. So we call the reactive part of the molecule that we care about the degree of functionality. Here, degree or DF equals 1 for each molecule. Let me write this down here. Degree of functionality equals DF. So does everyone understand that these two monomers have a DF of 1? One reactive group. Good. Does everyone understand that these molecules have a DF of 2? R1 has a DF of 2 and R2 has a DF of 2, right? They have a reactive group on each end. We'll talk about what those are because they can be a number of different things. Okay. So for vinyl or addition polymers, you know that for polystyrene, we can make a polymer out of this. So you know what this monomer looks like. You are convinced that I can make an addition polymer out of styrene, which is the monomer here. What is the DF of this monomer? 2. It has to be 2. Otherwise, we wouldn't be talking about polystyrene, right? An electron goes one way, and an electron goes the other way. DF of a carbon-carbon bond equals 2. Don't forget that. And so this equals linear polymer. That is tricky. And the only way to remember it is that you make a bond going one direction, you make a bond going the other direction. And so you connect to 2 different molecules on each side of styrene. That's why the DF is 2. And that's why you can actually get a polymer. I'm going to draw it like this just to make things clear. That's why you can actually get a polymer out of this, right? Because if the DF was 1, if you're like, oh, the double bond just has the DF of 1, you could never make a polymer out of it. That's tricky. That's just something you have to understand. So ethylene glycol dimethacrylate or diacrylate looks like this. What is the DF of that thing? 4. 2 for double bond number 1, 2 for double bond number 2. All of a sudden my DF is 4. And I'll tell you right now, and I have a picture of this in a second, that anything with a DF greater than 2 gives you branched or cross-linked polymers. And I'll show you that in a sec. All right. Now, for step growth or condensation polymers, mostly we've done reactions like this. Plus I'm a polymer professional, so I can write down the monomers of PET quickly. If you could do it that fast, that's great, but you should be practicing this at home because you know these monomers together make what polymer? What type of polymer in general? Polyester, right? They actually make PET, and so you can go home and finish this structure, but we're going to make a step growth or condensation polymer, and this one is polyethylene terephthalate. Whoops, let me just put the minus sign in a place that's accessible. So that's great. What's the DF of these monomers? What's the degree of functionalization of ethylene glycol right here? 2. It's only 2, right? 1 functional group, 2 functional groups. Same thing with the dipic acid. One, and that's not a dipic acid. With terephthalic acid, 1 functional group, 2 functional groups. And so because this is a condensation polymer, and we're going to build a repeat unit out of both of these molecules, the degree of functionality of each needs to be 2, and we're still going to make a linear polymer. And there's going to be other pictures of this. This is something we're going to practice over the next couple of days. But this is something that you should think about, that every monomer that you use has to at least have a DF of 2, otherwise you're not going to get a polymer. Yes?
So what about the C double bonds in the actual aromatic ring?
Yes, those are aromatized, so they don't have the same reactivity as a vinyl double bond. So we don't touch those. Yeah. Yeah, aromatics are special because they're more stable than your garden variety double bond because of the aromaticity. Any other questions? All right, we're just introducing it today. You know, this is going to be something you have to work on, but it's something you want to start to get comfortable with. So for a linear polymer, DF of all monomers has to be 2, exactly 2. If it's 1.9, you're not going to get a linear polymer. You're just going to get some short chains. If it's 1.99, you're just going to get some longer chains, but you're still not going to get polymer. So it has to be DF of 2. Even if we take something like this terephthalic acid and we react it with HOCH2CH3, the DF of terephthalic acid is 2. What's the DF of ethanol right here? 1, right? Is that going to form a linear polymer with terephthalic acid? No, no polymer with ethanol plus terephthalic acid because the DF of both monomers in a step growth polymerization has to be 2. And you'll get a linear polymer, always. You won't get any branching. You won't get any cross-linking unless you do something else. And so you're always going to get a linear polymer as far as you know right now if the DF is 2. Yes?
So if one was 2 and one was 3, then we wouldn't get any.
Less than 2, you won't get anything. If it's 2 plus 3, or if the average degree of functionality is greater than 2, if it's 2.1, if it's 2.001, if it's 2.5, if it's 3, if it's 5, you're going to get branching and networking like this. So higher than DF of 2, you get branching and networking or cross-linking. Remember, network equals cross-link. And so you see for a monomer with this little funny shape, there's 3 reactive points on there. And so you're going to get a lot of branching from that. Here's a DF of 2 plus a DF of 4. You're going to get branching from that. Here's a DF of 2 plus a DF of 3. You get branching. And eventually the branches meet each other and make a cross-link network. But that's a different thing that we'll talk about. For now, DF less than 2, no polymer. DF equal to linear polymer, DF greater than 2 on average, branching and networking. Yes.
So when you say like a DF of like 2.1, are there monomers that have DFs that go into the decimals, or is that just like the average?
Great question. It's always an average because you can't have 0.1 of a functional group or 0.1 of a monomer, right? So a DF of 2.1 would be something like if we had, say, 90 mole percent this, and then 10 mole percent of this. So this is DF equals 2. This is DF equals 3, 10 mole percent. So our overall DF average equals 2 times 0.9 plus 3 times 0.1. And I think that equals greater than 2, right? Something like that. Yeah. So it's always, since we're talking moles, since we're talking reaction, it's always the weighted molar average. Is that cool? Yeah. Any other questions so far? Okay. You can get out your clickers. We're on C and D. Clicker questions sometimes are easy, sometimes they make you think, but they always are designed to take attendance because the university asked me if you're here or not. So power button, and we're always CD this semester. All right, what's the DF of styrene? Maybe we'll get to 50. Getting close. All right. Usually when we get to 50, that makes me happy. So yeah, the functionality of styrene, as we just talked about, last chance, bring in. As we talked about is DF2. So my point on this. Great. Okay. That's important to remember. I'll ask you about that. It's important to know the difference between addition and step growth and how we count DFs. And so that will be something that we continue to work on. The other thing that we need to think about is this issue of equal reactivity, or the principle of equal reactivity. And now this is just a concept that you're going to have to commit to memory, just like a vocab word. You know, there's not lots of types of questions I can ask you about the principle of equal reactivity. But what we're going to say in this class is that no matter what the molecular weight of the polymer is, short chains, medium chains, long chains, this star is denoted by growing end or reactive group. And remember what a polymer looks like when it's growing in solution. Let me get fancy here. Well, maybe I can't get fancy. Oh, blue. Great. Remember, there's monomers out here floating in solution. There's a monomer here. There's a monomer here. There's a monomer here. There's a monomer here. And so this thing is a growing chain. And it's going to react at the growing end with monomers. Or sometimes we call these unreacted monomers because they're not part of the chain yet. And so when that chain is growing and it's short, it's reacting with monomers. And that reactivity, the kinetics of that reactivity, the organic chemistry reactions that it does is the same no matter what the molecular weight is. And that's called the principle of equal reactivity. That's just something, an assumption that we need in order to develop some of the equations we're going to come up with. Now, in your advanced polymer classes, you'll talk about why that doesn't hold at high conversion and other things like that. But for now, any growing chain end or any molecular weight or any reactive monomer, because initially you'll start with something that looks like a monomer that's ready to go. that all has the same reactivity. So when I ask you a question about the principle of equal reactivity, basically you're going to have to state that principle in your own words or provide an example. This is a nice way to do it. Any questions about that? Yes. Yeah, so the principle of equal reactivity means that no matter what the molecular weight of the growing polymer is, the reactive end group has the same reactions and the same reaction kinetics as any other molecular weight. So in essence, what it means is molecular weight does not matter in terms of reaction. All right. And we saw this diagram before. I don't love this diagram, but it's either in the book or it's a common diagram that people use. So chain polymerization, remember, usually starts from one end and grows like a chain reaction. And step polymerization, you go dimers, trimers, tetramers, etc. We'll add some detail to this as we go on, but it's just useful to compare and contrast. All right, and we've talked a lot about this. All right, step growth or condensation polymerization or polycondensation. We're going to focus on that for the next few slides. So remember, we're talking about this part of the curve. We're talking about the step growth, build up of molecular weight. It's nice and slow. And so when we do linear step polymerization, we need monomers with the DF of 2, right? So this one, oh, all right, I think we're back in business here. Hold on, let me get the slides up. It's going to be a hassle stitching these movies together, but that's how it goes. All right, I think we're back. Let me make sure we're recording and not muted. All right, that's cool. Okay, so we're going to make linear polymers by polycondensation, and we can use a couple different types of monomers. We can use these difunctional monomers, as in this example. So A, R1, if we want to put it there, and then B, R2, and they each have a DF of 2. So this is like ethylene glycol and terephthalic acid, just as I showed you before, a diol and a dicarboxylic acid. So every monomer has a DF of 2, A reacts with B, and you get chains like this. And of course you have another AA, then you have another BB, then you have another AA, etc., etc., etc. So that's called an RA2 plus RB2 type step polymerization. You can call it AABB if you want, but this is the general flavor. Now, one sec. You don't always need to have an alcohol and a carboxylic acid or an amine and a carboxylic acid. We're going to use one polymerization where alcohols react with alcohol. So if we take OH, CH2, CH2, come on. OH plus the exact same molecule, Does anyone know what the condensation product is of two alcohols? What's the small molecule that I can probably spit out of the condensation? Water. And so what do I get when I spit out water from the condensation of two alcohols? What's the functional group called? Ether, right? Polyether. That's the example for Ra2. And I have to tell you that A reacts with A, because if A reacts with A in this example, there's going to be all sorts of messy stuff going on, right? I have to tell you A reacts with B, build up the polymer. But in this case, for polyethers, A can react with A, and so I get a polymer structure that looks like this, and that's how I build a polyether. And polyethers are really important in battery technology, so they're a widely studied class of materials. Yes?
So are there special conditions for the polyether reaction to occur?
Yes,
So they don't occur in the Ra2, Rb2 step?
That's right. If these are ethers, right, because we can use ethylene glycol right here, we use different reaction conditions to get different reactions. And it will be clear what I'm asking you for on the exam. Yeah, good question. You had a question?
Yeah, I was just wondering, this all your oral linear, correct?
These are all linear. That's a great question, because in every case, DF equals 2. All linear polymers. There's nothing with DF of 3 here. And the other case is that you could have an alcohol on the same molecule as a carboxylic acid, and you get something called an AB polymerization, where the monomer can react with itself. But still, you have a DF of 2. So the only polymer you can make is a linear polymer, and that looks like this. So this will take some time to sink in, but these are all linear step polymerizations. DF equals 2. And so we will practice what types of chemistry and what types of monomers work in these different types of linear step polycondensations. So this is a key thing you're going to need to know. There will be a couple questions on this on the exam. I'll give you some monomers. You have to tell me what's going on. The answer, I think, will be pretty clear, but this is important because now there's a few different ways to make these step polymerization polymers. Any questions? Yes?
Are step polymerization and step growth polymerization same thing?
All the same. Step growth, polycondensation, exactly the same, right? There's only 2 different types of polymers that we've talked about so far. Addition with vinyl double bonds and polycondensation. That's it. There is no third choice right now. All right, you can get out your clickers to confirm. All right, we're going to introduce another functional group. This is called polycarbonate. And the key for a carbonate group is that there's an oxygen on each side of the carbonyl. Notice those oxygens are not on the same side. It's not oxygen, oxygen, carbonyl. That's not anything that we're going to talk about in this class. This is a polycarbonate, and this is a functional group that polycarbonate plastics use. And so lots of polycarbonate is made using bisphenol A and phosgene, which is actually a nerve agent. I don't suggest you do this in the lab. And so if we're going to make this polycarbonate, and this is the polycarbonate that everyone was concerned about with bisphenol A and baby bottles and everything else, remember, here is our functional group, oxygen, carbonyl, oxygen. So what type of reaction is this? You can click it. Oh, good, we're already at 40, it's great. 2 different monomers, each has a DF of 2. And so it's Ra2, Rb2, because here's 1, 2, that one's easy. And it turns out these are the reactive chlorides, 1, 2. So that's the right answer. Oh, let me stop the, oh, great, we got to 54.
Great answer.
There you go. Remember, you can always correct your answer, although we're not looking at right answers. We're looking at were you here or not. But this is what you're going to have to do going forward. Figure out what the polymers, figure out what the monomers are, and be able to classify. One last question before we go. Yes.
Now, will HCl be a reaction?
Phosgene is a very special group. And so that Cl is reactive because of the electron withdrawing of the carbonyl. It's a good leaving group. As you know, in organic chemistry, halogens like chlorine and bromine and iodide tend to be good leaving groups. Yeah. All right. See you on Wednesday. Don't forget to look at your homework and get geared up for the exam.
There are other toxic nerve agents that make good polymers?
You know, phosgene is the, let me